Another pollutant that comes from burning sulfur compounds, sulfur dioxide. Sulfur again is listed first, so that's the central atom. So S with its 6 valence electrons. 2 oxygens, each one again in group 6A, so it's 6 electrons. So here's 2 signals right there. So I'm going to put those right there. And then I got 2 pairs here. I'm just going to put this on the other side. I'm going to stop this plus and get up there. Okay, so this right here I'm going to focus on first. This is lacking 2 to be full. There's 2 lone electrons here. So we're going to get a double bond created right here. This, however, does not need any more. So this electron right here is going to migrate over there. And we're going to get a single bond between these 2 right here. So we got this and this. And then a pair of electrons right here. Okay? Now, notice, when I ask you how many sets of electrons there are, we now have on the central atom, and I will identify the central atom with the asterisk again. That central atom has 1, 2, 3 sets of electrons. That pair is a grouping, a location where they are found. So there's 3 different locations around the sulfur where the electrons are found. So again, we have 3 sets of electrons. And as we showed before, that means that the bond angle is 120 degrees. Now, here's the kicker. Okay? How many bonds do we have around that sulfur? Now it's different from what we had the last 2 times where they were the same. We only have 2 bonds here, a single bond and a double bond. Okay? So I'm going to put 2 bonds. Now remember, this structure, because of the 120 degrees here, is going to look something like this. Right? So, if you had something attached here, that'd be triangular, but there's nothing there, just a pair of electrons. You don't see anything. So what you see here is a structure that is not linear. So the geometry, now I want you to understand that people are paid a lot of money to be in charge of naming compounds, structures, whatever, in chemistry, both organic and inorganic, and everything in between. In this particular case, they had to come up with a name for this structure. So they gave it a name and they called it bent. Lots of money paid for that. Bent. Alright. So, put this back in the structure. 3 sets of electrons, automatically 120 degrees. Remember, this is on that printed chart in your script. Now you have 2 bonds, and we identified this as the bent because we're clever. Now the next one gets to be a little tricky because now we're going to get into the 4 sets of electrons around the central atom. Okay, so we're going to start off with the simplest of the organic compounds, which is methane gas. Methane starts off with C, that makes that a central atom. Okay, so carbon. Carbon on the periodic chart is in group 4A. 1, 2, 3, 4. Hydrogen is in 1A, has 1 electron. So we're going to put the 4 hydrogens, a single electron, facing the single electron of the carbon. And this is what you get. You make a bunch of single bonds around it. And then this is the linear form of the Lewis-Dot structure that we got from the circular rough draft. And as you can see, there are four areas around the central atom, which is common, so I'll put my asterisk right there. That's my central atom. I have four sets of electrons. Now, I'm going to attach a geometric shape that helps you identify what this thing looks like. This looks like it's going to be 90 degrees because everything's equally spaced apart on plane. However, if you go above the plane or below the plane, this angle right here is 180 degrees. This angle right here is 180 degrees. So 90, 90, 90, 90, 180, 180 does not sound equal to me. It's not. So they're going to buffet each other and get to such a point where they're evenly spaced apart. And like I said, I'll attach the diagram so you see what one of these things look like as far as the geometric shape. But this creates an angle not of 90 degrees, but more than 90 degrees. It has to be somewhere between 90 and 180. And so the line angle is 109.5 degrees. So anytime you have four sets of electrons, you're going to get theoretically 109.5 degrees. In actuality, it's slightly off because of various reasons, but we are going to keep it at the 109.5 degrees of prediction. Okay? Now, at this point here then, we've identified the sets of electrons, we have a new bond angle, a weird thing, and when I show you, there's a geometric figure called a tetrahedron, which is a four-sided figure made of equilateral triangles, but the angle with the center to each point is 109.5 degrees, and hopefully you'll be able to see that if you take a gander at that molecule or that molecular structure or geometric shape. All right, now, how many bonds do we have? We have 4 bonds. And when you have 4 bonds, you have that geometric shape that I was showing you, and you're going to take a look at it. But that is called a tetrahedron. So the shape is considered to be tetrahedral. Now, to help you remember that, if you've ever played the game Tetris, you know that the number of blocks that each figure has is 4. A Russian designer, programmer, came up with this game, and he came up with this term, or used the term. He may not have come up with it, but he's the first that I'm aware of that actually used this term to any public awareness. But tetra means 4, and therefore tetris is a number of blocks, what they call tetrahedrons, I think they call it, shapes of 4 figures. And that's maybe one way to help remember the name tetrahedron. So, go back to the chart. We now have 4 sets of electrons, 109.5 degrees, 4 bonds, and this is tetrahedron.